term because the job title hasn't been around very long. Research software engineers partner with researchers who are writing their own software to ensure that those software are sustainable in terms of being useful in the long term, that their research results are reproducible. You may be aware of the reproducibility crisis in certain fields in science, and to use the Software Sustainability Institute's tagline, better software, better research. So that's what we aim to do. This presentation, there's the clicker. This presentation is not just the work of myself. I have a very small part, but it was the research software engineering team led by Dr. Christopher Woods, who's done most of this work in collaboration with our good friends at Oracle, who provide the Oracle cloud infrastructure which we've been using. So this presentation is mostly in two parts, but I'll start off with a little bit of scene setting about on-premise clusters. You may have an on-premise cluster supporting your research users in your institution, and the workflow for a user looks like this. They're sitting at their workstation or their laptop here on the left-hand side, and they want to access this resource here on the right. This is the University of Bristol's Blue Crystal Phase 4 supercomputer. So they fire up an SSH session, they log into the login node, they upload their data, they write a small job script to describe how they want the job to run. They submit that to a queuing system, and then they wait in the queue with potentially hundreds of other users and potentially thousands of other jobs until such time as a resource, because all these jobs are being continually added to the queue and continually being removed, until such time as there's enough resource for their job to run. They wait while their job runs, and then they either analyze the data in place on the HPC system, sorry, HPC high performance computing on the HPC system, or if it's small enough, download it back to their workstation and analyze it there. And this is a model of high performance computing that hasn't changed in decades. If you were doing HPC in 1980, it would have looked exactly like that, except you would have said Telnet instead of SSH. So I'd like to introduce the work of my colleague Matt Williams. So I've done a small bit with this with the testing and support, but Matt's done most of the work here on an open source project we're calling Cluster in the Cloud. So it makes use of a couple of technologies, Terraform to provide the initial infrastructure in the cloud, and Ansible to configure it. To provide a resource for researchers to use. So the URL on the bottom left-hand corner is a read the docs file for it. It's a tutorial. It tells you how to go from some credentials in a cloud service to a running, auto-scaling, heterogeneous cluster, which I'll explain what that means in a second. So if you go to the docs, it'll tell you to clone a Git repository and edit the configuration file where you put in the credentials, and then you run Terraform apply. What that does in the background is configures networks in your cloud provider, configures storage, and it configures a virtual machine which does both the management of the cluster and provides the login. And so once all that's finished, takes about 5 or 6 minutes, then you can log in, the researcher can log in from their laptop. And so that again looks very similar to how they were using the on-premise system before. Then they submit their job to the queuing system. This is where it's a bit different, because there's now not currently anywhere for the job to run. So the queuing system we're using is called Slurm. It's cloud aware, so it knows how to talk to different cloud providers' infrastructures and provide, well actually we had to glue some bits together to make that work, but it has a concept of cloud nodes, and so when there's a job ready to run but nowhere to run it, it fires up a virtual machine. So here in the Oracle Cloud we're using the bare metal machines. A BM standard 2.52 was the ones we first started working with. Those are the Intel Skylake nodes. So now the job is running on that first compute node. The researcher's got a campaign with lots more jobs to run, so they continue putting jobs in the queue. and the system continues to fire up nodes up to a configurable limit. So you can say, you know, my service limit is 10 or 100, or we haven't had anybody use 1,000 nodes yet. But you can put a hard limit on this, but it will keep, as you keep adding jobs, it will keep providing the resource needed. When a job's finished, node turns off. So we have this in a configuration setting. It's 15 minutes by default, because that's about the amount of time it takes for somebody to go have a cup of coffee, come back, decide all their jobs were wrong, and resubmit them again. But when all the jobs are finished, it turns off all the nodes, and you drop back to just having your storage and your login node. And so the benefits here are, compared to an on-premise system, which you might have a procurement cycle of 5 years, you decide how big your system's going to need to be, you buy exactly that size system and leave it in your data center for 5 years, and then put it in the skip and buy a new one. This, you can scale the size of your compute resource to the size of your load. When you're not running jobs, the nodes are turned off, and so you're not paying for them. We do recommend people leave the login node on, which is why we recommend they use the smallest VM size possible for that. The advantage here is that you don't need to retrain the researchers, because it looks exactly like their on-premise cluster. They just SSH to a different place. Bit of work we've just done recently is to enable Singularity. Singularity is the HPC version of containers, or the HPC version of a container runtime. So it will support Docker containers. The HPC system admins don't tend to like the permissions model of Docker, so that's why they've replaced it with Singularity. And so yes, this has been very useful for our researchers. So here are some of the projects we've done with it. The first one was the nicotinic receptor. So we're looking at signaling in cells, and that used a piece of molecular dynamics software called GrowMax. So this particular job was high throughput computing, so it didn't need particularly fast or low latency connections between nodes. We just fired up 100, I'll get to this on the next slide actually, 100 52 core nodes. Second project, Cryo Electron Microscope, I also have a slide about. That was actually the second one we completed, but the first one we started. That was what was the impetus for developing Cluster in the cloud, because the researcher had access to cloud resources but had no idea what to do next. So that's where this project came out of. We've done a project with a piece of software called BUDE, the Bristol University docking engine, which describes how proteins fit together. And that's a GPU application. Our on-premise system has 64 GPUs, so if somebody wants more than 64 at once, this is a way of getting it. There's a medical physics application we've been looking at. So if you're receiving beam therapy, it's critical to know how much radiation the patient's received. And so you can put a measurement device in with the patient. So this is built out of silicon, the same sort of thing as silicon chips. And this was calibrating and modeling that work. We've also been doing some work with Royal Holloway and Surrey universities on carbon capture and sequestration. So as we all know, putting too much carbon dioxide into the atmosphere is a bad idea. One possible thing you could do with it is not put it in the atmosphere, capture it, put it in the ground, but to analyse, how the carbon works in the rocks, they need to do finite element analysis. That's where that was the first user who had a use case for using Singularity. We are also working with researchers in the LZ consortium who are looking for dark matter. So a wide range of subject areas we can deal with our system. So back to the first project, GrowMax, the nicotinic receptors. We actually do run those jobs on our on-premise system already, so we know how long they take. To simulate 5 nanoseconds of real time, it takes 17 hours wall clock on Blue Crystal Phase 4. At the time this project was run, this is about 18 months old now, that was our most advanced HPC system at the University of Bristol. We now have a smaller system with newer nodes, but that was 17 hours on Intel Broadwell, and the user had to compete with the other 1,000 users at the University of Bristol who use the HPC. So we didn't run the campaign on Blue Crystal Phase 4. We estimated it would have taken about 3 months. In contrast, with the Oracle Cloud infrastructure, we had access to a newer CPU, that was new at the time, the Intel Skylake. That's where you get most of this benefit of the wall clock time reduction, because it's just a faster CPU. We stood up a cluster of 100 nodes that was just a personal cluster for that researcher. That group, there was one person really running the jobs. And so they could run 1,000 one-node jobs at once. We got access to the nodes at the beginning of the week on the Monday. We were ready to go and run jobs on Wednesday, and it was all done by the end of the weekend. And so the benefit here is if you have the means to purchase the cloud resource, you get much faster time to solution. The Cryo Electron Microscope is the thing on the far left side there. It's quite a large device. The technique actually won the Nobel Prize in chemistry a couple of years ago. It's an advance on the traditional electron microscopy, where you get a single image when you take the photo. In Cryo AM, it takes multiple multiple images of the protein as it's moving around, and so you get the protein from all sorts of different angles. That gives you a lot more information to work with, and you can get a lot more resolution out of it to identify the structure. It does, unfortunately, produce terabytes of data, so that's the challenge. The other challenge with this one is that the image processing workflow uses a piece of software called Relion, which is a workflow which ties together all sorts of other pieces of software, each of which have different performance characteristics. So some work better on CPUs, some work better on GPUs, some work better on high memory machines. And so we were able to, using our cluster in the cloud software and the Oracle compute infrastructure, change the nature of the cluster during the job to fit the job size. So this is the adama protein. It's a synthetic protein. It's being used to make synthetic vaccines. The advance here is the current model for making vaccines requires them to be refrigerated from when they're produced to when they're used. You've got to maintain the cold chain all the way, which is not hard in a first world country, but in other parts of the world it's very hard to make sure that the vaccine stays refrigerated the whole way. And so with the synthetic vaccines, they can be kept at a much higher temperature, so those are much more convenient. Doing this work, generating the structure of this protein from the cryo-electron microscope took 217 pounds, calculate. So cost effective. What we've been doing so far though is a lift and shift. We've taken our on-premise cluster and essentially replicated it node for node, byte for byte in the cloud. And the same way, when radio technology developed sufficiently that we could have mobile telephones, the first thing we did was we lifted and shifted the technology we had into, well, the ways of working we had into the new technology, but that didn't really make the most use of it. So nowadays we know that a smartphone can do a whole lot more than just make phone calls. Similarly, with the cloud, what more could we do if we use the technology that the cloud enables rather than just trying our previous ways of working? And so we had a cluster and we had one user and they still had to go into a queue. So that's a bit weird. Is there a better way of doing it? So second project I'd like to introduce is the work of Christopher Woods. It's also open. Did I mention the cluster in the cloud? It's open source, MIT licensed. Acquire is also open sourced. It's a piece of middleware that does AAA authentication, authorization, accounting, and identity management. Christopher's feeling is that the fundamental building blocks of the cloud, the fundamental abstractions, serverless functions, and object store. So Acquire is built on serverless functions and an object store. I'm not going to show slides of that because that's all a bit boring, but I will show you a slide and a video of what it enables. We're just going to skip over the video to talk about Jupyter Notebooks. Is anybody in the room familiar with Jupyter Notebooks? We've got about a third. For the other 2/3, these are loved by data scientists. The concept, I think, came out of Mathematica, a piece of mathematics software, and the idea is that you, in the same electronic document, you combine textual descriptions of what you're doing, the source code to do it, the output of the results, and you combine that all in one reproducible package. And so down the bottom left is the jupyter.org website where you can find out more. The second URL, notebook.biosimspace.org/hub/login, is actually live right now. That's sitting on a sitting on a Kubernetes cluster in Oracle, using the AAA system that Christopher's developed. It's currently using Christopher's money, so it's live. If you go to it right now, you can start a simulation. Just don't start too many simulations, otherwise he'll run out. So we'll go back and have a, this might be, if you've never used a notebook, this might be a bit academic, so we'll go back and have a look at, if I can figure the video. So each of these things is cells. The thing with the blue bar is the one that's running. We can have a look at this simulation. It's got 631 molecules in it. We can kick it off where it says bss.md.run. So we can now interactively look at the running job, which is a little bit different to the batch processing we were doing before. We can look at the runtime, we can look at the total energy of the system. If you're a molecular dynamics person, this will make sense to you. It doesn't make much sense to me. Simulation's still running. We're still, and you can see the values are changing. The total energy went up there, I think up. You can also look at, you can produce graphs of the data, and that if we re-execute that cell, you'll see that because the simulation's still running, the data has changed. Jupyter Notebooks don't by default have this, but you can add it in. You can do a 3D visualization of the molecule. So the one we're simulating is that thing in the middle. Around it, all the red and white is just water in a box surrounding the molecule. And we can have a look at how the molecule moves. So that's the point of doing these things, is to look at the root mean square deviation per frame. And so there are the results of that simulation that was running. So that was using a Jupyter Notebook locally for the researcher and compute resource remotely in the cloud, accessed via the Acquire system. So yeah, we think these are great. They're almost a new approach to writing a paper. It's a dynamic scientific paper. Here we're looking at a much bigger visualization, a much bigger molecular system than the last one. So all the data is stored in the cloud, and it's just sending enough across the internet, enough information for the browser to be able to draw the atoms using WebGL. And so we think this is, revolution might be too big a word, but it's definitely a new paradigm for scientific computing that can be enabled by using cloud resources like this. The traditional method of simulations and shared multi-user systems with batch queues, we still have, but we can now add to it notebooks, visualizations, data analysis, interactive scientific papers, which we're characterizing as on-demand computing to distinguish it from the batch computing. So if you think of broadcast television as batch television, then on-demand computing is the Netflix of simulation. So So I've been asked to tell you about a bid that we've put in for the EPSRC Tier 2. So in the Branscombe pyramid of high-performance computing resources, Tier 0 is the pan-national systems. So for us, it would be the PRACE systems in Europe. Tier 1 is the largest HPC system you've got in the country, which is the Archer system, the Archer service in Edinburgh. And there are a number of Tier 2s spread throughout the country. We're in fact currently on the second round of funding for Tier 2s, and they've just put out a call for a third round of funding. And so we're putting in a bid called Breeze, and it is combining the two pieces of software I've talked to you about, Acquire for the access to the resources and Cluster in the cloud to provide the compute. There are 4 universities involved with this bid. We have support from major public cloud vendors, and we will hopefully hear at the end of the month whether that's been successful or not. I'm not sure how I'm doing for time. Good, because this is the last slide where I thank people. So the Research Software Engineering Group, as I mentioned, Christopher Woods, Andrew, myself, Lester and Matt. Biosim space, so all the molecule visualization stuff, all of that work is a collaboration between University in Edinburgh and Bristol. So some of those people are from Edinburgh and some from Bristol. The team there that says HUGS, I haven't talked about that, but it's the Hub for UK Greenhouse Gas Science, and that is going to take the Acquire system exactly as we saw with the Biosim space and convert that, or take it across into different scientific disciplines. That's atmospheric chemistry. So the idea is to prove that this approach works whatever the field you're dealing with. Christopher is funded by the EPSRC, and some of the projects are also funded by NERC, and none of this would have been possible without the support we got from Oracle with access to their cloud resources, access to their engineers, and so we would like to thank Jenny Sy-Smith, Phil Bates, Gerardo, Chad, etc. And I don't have a slide that says questions, but I will happily take questions.
I think you've baffled us all, Christopher. That was fascinating.
Good. So I'll be around until 4 o'clock, so lunch and afternoon tea, and the Oracle people will be at their stand, and we'd be happy to chat.
Excellent. Thank you very much. Now, if we can just have a big round of applause for Christopher.